Hello, welcome to another video of Thermodynamics. In this video, I'm going to explain how the theoretical cycle of a spark ignition engine is analyzed. When it comes to the theoretical thermodynamic cycle of a spark ignition engine, we may need a little bit of understanding what actually happens in a spark ignition engine. So a spark ignition engine can be modeled as a simple piston cylinder device, which of course has two valves on top of it. And there's a piston, which is connected to the crankshaft in actual conditions, moves up and down inside the piston, inside the cylinder, sorry. So when it moves down, one of these valves or one of these valves, intake valve opens, and the draft of air comes in with a mixture of fuel, and then the piston moves up in the next run, and the gas fuel mixture or air fuel mixture is compressed. Once the mixture is compressed, uh, so once the mixture is compressed, there's a spark plug that fires, and air fuel mixture is burned inside. That creates a high temperature, high pressure gas inside that force the piston to move down fast, and that's a downward motion again, the piston. So that's also called an expansion. So we had basically an intake process, and then compression process, and also just at the end of the compression we had a fuel burning, and actually that can be modeled as a heat uh, absorption or heat in process, heat in, right? And then all of a sudden, that when the fuel is burned, the piston moves down. That creates that's work creation process or expansion process. Expansion process. And then the fourth one is a uh, exhaust process. And according to AI standard assumptions, we model this exhaust process as a heat rejection process, heat rejection process, because all the heat inside the engine is expelled in that during that exhaust process. Now, these four processes that actually happens in the engine is more complex and involves a lot of irreversibilities based on our AI standard assumptions that we're going to actually talk in the class. Based on the AI standard assumptions, we neglect all the complexities and consider all the processes involved in these cycles. All the heat engines are internally reversible. Okay, and as you know that, so we consider that all the processes are internally reversible. And then also we assume that the working fluid is air throughout the cycle. That is not the case actually. Working fluid is air throughout the cycle. In fact, we know that it burns and different gases. The gas is not actually only air. It consists of fuel at the beginning, and also once when it's burned, it's burned gases, flue gases. But we assume that it is air throughout the cycle, and we model the combustion process as a heat addition process, right? And the fourth one is the exhaust process. Exhaust process is modeled as a heat rejection process. So these are called air standard assumptions. And also, if we add the fifth one, that is the constant specific heat assumption, that is, we consider that we assume that Cp, Cv are constants at their values uh, at 300 K. So we consider Cp and Cv a constant, and we assume that Cp and Cv equal to value at 300 K, because although the temperatures inside the engine changes a lot. So those are called, these four are called air standard assumptions. And with this one, plus this one, we call cold air standard assumptions. So now we know that the intake process and compression process, and then compression process at the end, it's a heat addition process because the combustion takes place, right? Plus combustion. The combustion process is a heat addition process. And then you have expansion process and also exhaust process, which is a heat rejection process. In this case, the intake, when it comes to theoretical analysis, in theoretical analysis, we consider there are four different processes. So if I write the Otto cycle, these are the processes that we use to model the actual processes. Process 1 to 2, the first process uh, is named as internal reversible adiabatic compression. So internal reversible adiabatic compression is isentropic compression. And also 2 to 3, the second process is, now once it's compressed, you have the combustion. So internal reversible constant volume heat addition. So internally reversible constant volume heat addition. Constant volume heat addition, because we assume that um, the, the combustion process takes place very quickly, such that there's no time for the piston to move down quickly. So that means the volume in between the crown of the piston and the top of the cylinder, the crown of the piston and the top of the cylinder, this volume, this is the piston at the top, dead center. This is called TDC, top dead center. This volume remains constant during the combustion process, and it quickly takes place. And 3 to 4 is known as, it's an isentropic expansion. This is the process in which that work is created. And then 4 to 1 is internally reversible constant volume heat rejection, which is also equivalent to the exhaust process. Now, if I were to draw a TS diagram, this, right, a TS diagram, constant volume process of a TS diagram is shown like this. So the first process is constant, these are constant volume lines, so constant pressure lines are the same. That's called TS diagram. Let me start from the beginning so that listen to you. That's a TS diagram. And the first process, isentropic compression, compressed isentropic, entropy is the same. This is 1 to 2. And 2 to 3 is isentropic, internally reversible constant volume heat addition. So heat addition, this is what constant volume, it's like this. And then you have constant volume heat rejection, isentropic expansion. So it's expansion, 3 to 4. And then you have 4 to 1 is constant volume heat rejection. So the cycle looks like this on TS diagram. Now, often we use PV diagrams when it comes to Otto cycle. That's much popular in when it comes to uh, Otto cycle analysis. So we're going to use that as well. So most probably you may want to use PV diagram than you use TS diagram. So if I use the ideal PV diagram for this, that's much more, makes more sense than TS diagram. So you have the compression process. In the compression process, your volume is, this is the maximum volume, that's called V1, and this is V2, right? In the compression process, the volume reduces and pressure increases. That's your P2. This is 1 to 2. And then you have a constant volume heat addition. When heat adds into that, pressure also increases. Volume remains constant. And then at this point, exhaust process starts, expansion process, piston comes down, volume expands until V1, the bottom dead center, and that's 4. And 4 to 1 is another constant volume heat rejection process. It's like this, right? Now, this is our PV diagram. This is this is TS diagram, and this is PV diagram, right? Now we wanted to find, we want to analyze this. That means we want to find the uh, efficiency of the Otto cycle efficiency. So let's see the theoretical efficiency. I'm going to draw a PV diagram just for you to see. This is 1 to 2 is compression, 2 to 3 is constant volume process, 3 to 4, 3 to 4 is 3 to 4 is expansion process, isentropic expansion, and 4 to 1 is constant volume process, right? These processes are isentropic. Now let's see what is the thermal efficiency. Thermal efficiency is given by work out divided by heat in. Net work out, so work out net, and this heat in. Now, network output. Now, this is a closed system. It's a closed system, works on a cycle. So if you have this closed system, it's a little distance in the device, moves from state 1 to 2, right? And 2 to 3. and 3 to 4, 4 to 1. This is 1, 2, 3, 4. In the first process, it's a compression process. That means 1 to 2, work addition, work in. And 2 to 3 is a heat in process, Q in. Right? And then this is work out, 3 to 4. And 4 to 1 is a heat out, right? Heat out. Now, if you wanted to find, uh, if we apply the first law of thermodynamics to the entire cycle, first law for the entire cycle, delta U equals Q minus W. So delta U is the initial final internal energy minus initial internal energy. Final initial energy is U1. Initial internal energy is also U1 because it's on the cycle. Why did we write this equation? Because we analyze a closed system. And Q, we have Q in minus Q out minus W in uh, minus W out, right? W out, and you have uh, so minus W out uh, minus W in. This is our W net out, which is equal to Q in minus Q out equal to 0. Now we can solve for W net out. Net out is equal to Q in minus Q out. Now we can substitute to this equation 1, right? Net out thermal efficiency is equal to Q in minus Q out divided by Q in. Now we get 1 minus Q out over Q in. Now it's just a matter of finding what is Q out and Q in. Just a matter of finding what is Q out and Q in. Now to find Q out and Q in, I'm going to apply, first is I can find Q in. To find Q in, I apply first law for process 2 to 3. That's where actually Q in takes place. Right? This is a Q in. Right? So I can delta U is equal to Q minus W. Now this is a constant volume process. W is 0, constant V process, constant volume process. And then we have Q in equal to U3 minus U2. U3 is the final and U2 is initial, right? U3 minus U2. So if I apply the constant specific heat analysis, it's Cp T3 minus T2. Cp T3 minus T2. Sorry, Cv T3 minus T2, sorry. And MCV T3 minus T2 because du is equal to Cv dt, okay, for ideal gases. And one of the assumptions that we use here is that air is an ideal gas. Air is an ideal gas. Yeah, it's an ideal gas. Now, Likewise, I can apply first law for process 4 to 1, where I can find the heat out. So Q delta U, Q minus W, W again 0, same reason, constant volume process. And I can write U delta U is equal to U1 minus U4, final minus initial equal to Q1 to 4 or Q in. Now Q in is equal to, I can again use the ideal gas assumption, Q in is equal to MCV T1 minus T4. Now I have Q in and Q out, and I can substitute to the equation. Thermal efficiency is equal to 1 minus Q out over Q in. This is 1 minus MCV T out is T1 minus T4. And then we have MCV T T1 minus T4, and then we have MCV uh, MCV uh, 3 minus T2, T minus T2. One other thing that we need to make sure that this Q out, when you write T1 minus T4, it's going to be a negative value. Since we're getting a ratio, Q out should be taken as its absolute value. So I'm going to switch these T1 and T4, the next step, 1 minus MCV, that just because we need the positive value for that. MCV T3 minus T2. And I can cancel this out, right? And I also know that for the isentropic processes, since process, let's say this is equation 3. For the process 1 to 2, I can write it's an isentropic process. 1 to 2 is an isentropic process. T2 over T1 over T2 equal T1 over T2 equal V2 over V1 over to the power K minus 1. And I can also write for the process 4 to 1, that is also, sorry, for the process 3 to 4, for the process 3 to 4, I can also write T4 over T3 is equal to V3 over V4 to the power K minus 1. Now this is an additional simplification because we need to model this equation, and there's a quantity that we can define as compression ratio R, which is actually a volume ratio V max over V min. Now if you go back and look at this cycle, what is V max? V max is the V1. V min is V2, which is equal to V3, and V1 is equal to V4 because these are constant volume processes. So going back here, I can write that R is equal to V1 over V2, which is also equal to V3 equal to V4. Oh, sorry, V4 equal to V4 divided by V1. V4 divided by, because V1 is equal to V4. So here, actually what we got is here is from V1 equal to V4, constant volume process 4 to 1, and V2 equals V3. V2 equals V3. So this should be 3. So from that, I can write for the equation 4 and 5, let's say 4 and 5, I can change 4 to T1 over T2 equals 1 over R A minus 1. And I can also write from 5 T4 over T3 equals 1 over R K minus 1. So what I'm going to do is I'm going to uh, take out T1 from the from this equation, from thermal efficiency equation. Now I can write 1 minus T1 T4 over T1 minus 1 divided by T2 T3 over, I can write that, uh, and from equation from here, these two equations 6 and 7, I can obtain that uh, T4 over T1. What I'm doing is actually, let me show you clearly. Um, the next page, let's take it to the next page. What I had was this T1 over T2 equals V2 over V1 K minus 1. And also I had T4 over T3 equals V3 over V2, sorry, V4 our K minus 1. From these two equations, I take, this is, what was the number? 6 and 7. 6 and 7. So I'll take 7 divided by 6, where I would take T1 over T2 divided by T4 over T3, which is equal to V2 over V1 K minus 1 to the power V3 over V4 K minus 1. From here, what we see is that uh, we know that V1 is equal to V4, right? V1 is equal to V4, so this cancel to this. And V3 is equal to V2. From the diagram, you can see that V1 is equal to V4, V2 equal to V3. So we can cancel those two here, and that's equal to 1. That's equal to 1. So we have T1 over T2 equal T, I just should have another, this is equal to 1 by T4 over T3. From here we get T1 over T2 equals T4 over T3. T1 over T3 equal T4 uh, T4 over T3. Now from that I can get from here T4 over T1 equals T2 over T3. T4 over T1 equal to T2 over T3. Uh, that gives me that um, which gives me that the thermal efficiency equals 1 minus T1 over T2, and T2 power uh, T2 over T3 minus 1 divided by T3 over T2 minus 1. Sorry, I made a mistake here. I think I mistakenly wrote that it should be uh, right here. I need should be corrected as T4 over T1 is equal to T T4 over T1, T3 over T2. So for when it comes to here, that's what we have from the earlier equation. I can write I can write T3 over T2. So that's T2. So this is equal to 1. So we have 1 over T1 over T2. So which is nothing but 1 minus uh, 1 over R to the power K minus 1. So the thermal efficiency can be written as 1 minus 1 over R to the power K minus 1. So this is the Otto cycle efficiency. Thank you very much for listening to this video, uh, and we'll discuss the further in the class.